by Professor Pennan, ourselves, our team, AIT solution engineers, student thesis, lab testing, everything, software development, everything is all directed towards performance-based design development. So we should have the most knowledge here compared in this particular field. So that's where our main strength is. And this is just for your information, what is performance-based design. Now we look at the performance of a structure and we want to see whether after an earthquake or any event, major wind or whatever, will the structure be operational or will it be damaged? Will we have to shut down for a while and then come back? Or will it be safe for life safety? Or will it collapse or not collapse? So we check the structure in this way. We don't check about other things, factor of safety or factors or bending moments and things like that. We check this way, right? Which is based on deformation and strains, right? So that's and a lot of our graduate engineers, they also work in AIT, continue to work in performance-based design in our office. And our thesis also, a lot of half the students are working on the performance-based design on tall buildings and other things, approximately. So, okay, last part of this first lecture. Building block of structural mechanics. What is structural mechanics? What is it based on? What are the key things that we use? Relationships between one and the other. We are just trying to manipulate these relationships to find our answers, because everything is related to something. But actually the problem is that we have something here and we want something here, but these two are not related directly at all. But this one is related to this one is related to that one is related to this one is related to that one, and this one is related to that one. So there are many relationships in between. So we use those relationships in some way to find what is missing. So we have 5-6 variables, and none of the equation connects them together anytime. But some equation connects these two, these three, and we just try to use different equations to find missing and finally solve our problem, what we are looking for. So these are the relationships that we are looking at. So basically we have loads and load effects, we have actions, we have deformations, strains, stresses, and stress resultants. These are our bread and butter kind of thing for structural engineering. This is what we can deal with, right? Anything else? Come on. Challenge. Anybody watched the program How I Met Your Mother? You watched? In that they say, challenge accepted. You know that? So you should accept the challenge. Anything else? No. Okay, so basically we are looking at, as I said, if I come back to that diagram again, we can find these relationships here. This one, stiffness is connecting them, analysis is connecting them, material model is connecting them, integration is connecting them, factor of safety is connecting them. So most of the things are connected by something with each other, and we can use that relationship to solve our overall problem of structural engineering by using those 5 or 6 parameters and relationships between them. So we are going to start, as I said, this one and move on to this one. These two important things we will do, and then we will do some other things also. Now we come to the first part, analysis. This is not the subject, the topic of this course, but I think we need to know where we are coming from and where we go. So that's why I want to make sure that we all understand. This is a spring model of a structure. So if there's a load, any load means anything. And this is a deformation, means anything. This could be temperature, this could be anything. It will cause an excitation or a deformation, correct? It's like a spring. So if you push the structure, it will deform, and the deformation will be proportional to the push, and that proportionality is spring stiffness. That's the difference between Newton and engineers. Newton ignores stiffness. We cannot. So Newton is talking about ideal situations which do not exist. They're very convenient. You can develop equation ignoring stiffness, ignoring friction in space. Doesn't happen. It's not real, right? So scientists and engineers differ in that way. But we have to deal with friction, we have to deal with stiffness. So there's a stiffness, there's a mass, there's an inertia. So when you move a structure or try to push it, it will deform. And deformation will be proportional to something called stiffness, right? Who can define stiffness in a good way? What is stiffness? I want non-technical. You should speak last. Let other people speak because you are teaching this subject, so I don't want you to speak first. Okay, no, it's okay. But okay, anybody else? Stiffness. Define stiffness.
It happens to the structure, to resist, versus something that happened with that member to resist something that outside from it.
Yeah, but what is the difference between stiffness and strength? Are they the same thing or different thing? But you are talking about strength. Yes. Stiffness. Anybody else want to try? Stiffness is the ability of the structure to resist deformation, right? Not strength, deformation. So stiffness is the resistance to deformation. So if you try to push something, if it has a high stiffness, it will not deform. It has small stiffness, it will deform. So stiffness is the ability of structure to resist deformation. Structure is trying to resist. Structure does not want to deform by its stiffness. But if it has low stiffness, it will deform. Sometimes low stiffness is good. Sometimes low stiffness is not good. Right? There is an interesting example of tree, two types of trees. A slender poplar tree or a big oak tree. So when the wind comes, slender trees will bend with the wind and come back, and after the windstorm is over, they will still be standing. They have low stiffness, right? But a big tree, big trunk, wind comes, has very high stiffness, but if the wind is strong enough, it will push it over and will fall down, right? So high stiffness sometimes can be good, but sometimes not good. Low stiffness can be sometimes good, sometimes not good. So our engineer's job is to find the right stiffness, right? And we will talk more about it. So stiffness is the property of the structure that resists deformation. And this property exists everywhere. So stiffness exists in material. Stiffness. Stress and strain are related to each other by yes, most constant or modulus. First thing, forget about constant. This is not a constant. What we think is a constant is not a constant. So definitely the modulus of constant is not a constant. Okay, so we will talk about that. Anyway, modulus of elasticity, we will call it from now on, right? Not constant. Modulus of elasticity, because it's not constant. It's a misconception. Modulus of elasticity is the stiffness of the material, correct? E, you all know that, hopefully. Young's modulus, yeah. I don't know if it's so young or not, but Young's modulus or modulus of elasticity. Not a constant, but okay. Measure of the material stiffness. Cross-section geometry, section stiffness. So what is the measure of the section stiffness? Not you, anybody else. I said not you. Anybody else? What is the cross-section stiffness? Moment of inertia. That's right. Area. These are the cross-section stiffness. Properties of the cross-section which depend on the cross-section. Good, right? So, but section stiffness is actually a summation of the material stiffness and the cross-section stiffness. So actually it is EI. Modulus of elasticity of the material multiplied by the moment of inertia of the member becomes the cross-section stiffness, because it has a material inside which also has a stiffness. So you cannot have a cross-section stiffness without adding the material stiffness to it. Correct? Like concrete section, same size, and steel section, same size, different stiffness. Because material is inside, even though same moment of inertia. Correct? Okay. Then comes member geometry and member stiffness. What is member stiffness? Who will give me the formula for member stiffness, or the sample formula? No, you can say, no, you can also say. Member stiffness. Ever heard of EA over L? Yes, correct. That is your member stiffness, because it has no cross-section stiffness, it has material stiffness, and member's length also in it. So EA over L is the axial stiffness of the member. It's so easy, so simple, so systematic. Material, cross-section, member. And what is the structure stiffness? Structure stiffness. Come on, it's okay. Say something. It's simple. It is the sum of all the member stiffness. Because if we have 10 columns, then if you add the stiffness of beams and columns and every whole structure in a certain way, it will become the structure stiffness. The more member, bigger member, more stiffness. So, as you can see, stiffness is gradually built up. Right? And stiffness is not a constant in any of these relationships. Let me show you now an interesting curve. And we are going to see such curves many times in this course. This is a typical FD curve. We call it FD curve, force deformation curve. This is how a real structure will respond, not what you have been taught before. So it will start from here when you apply, let's say it's a beam, and you apply the load in the middle, and then you measure the force.